Okay, and the second way of doing it is character-based method. This is also based on the base change. So the difference itself is not enough. So if you change from A to B, A to T, or if you change to A to C, it's going to be indifference now. And this method do something slightly different. And this is going to be a little bit convoluted. I'm sorry ahead of time, but I'll try to make it as simple as possible. And remember, once again, our goal is be a user. We're gonna try to understand the idea behind it and how to use them. If you are interested in more detail, I actually put the whole book chapters on this, and they have equations and like the real math behind it. You can read them, quite fun. But this is different from the other because before the other method, you only have one final answer, right? This one, you're gonna search a number of trees. So a number of possible trees, possible relationship, and you choose the best. So this is gonna sound a little bit weird, but this almost like Miss Universe type of contest. Have all these beautiful women from around the world, right? Beauty contest, and you find the best one, whatever that best is, and you have your own criteria, right? And there's a three method that can use that is called maximum parsimony, maximum likelihood, and basic inference. And we're going to cover how each of these work briefly, and we're going to try to do two of them today in the second part of the class. So why all this? So let's start with something closer to home. Murder woman. Like what? Ajahn, you are so sick. Like this is morbid. Well, like how many movies have you watched that have at least one murder woman? So it's I I mean, if you grow, I spend too much time in the US, and if you like sit down your TV and scroll any TV show, there are at least like 10 cop shows. And at the beginning of the show, it's like somebody die. Always like, come on, like just like Thai soap opera is always like, people fighting for slap and love and one pretty boy and too many pretty women fighting for one person. In the US, it's all like, whoa, he's died. How do we do that? Who's the bad guy? Oh, DNA quickly. Yay, father, murderer. So just think like this, like you walk into the room and you found somebody dead. You don't know what's going on. Well, you see it's murder because it's like being slashed. What is your instinct, right? So there's a belief. There's a general belief that most of the women, the murdered woman, usually killed by her husband if previously abused. There's a statistic back up to that. And because you find her pocket and you look at ID and you look up in the data, you found that this woman have reported abusive relationship with her husband before. It's like, suspect number one, husband. Right, they have in abusive relationship. She had bruises on her face before, and like statistically say that if she's been abused before, then she's likely to be killed by her own husband. And most of the domestic abuse actually by the person close to you. This is actually true, and kind of sad. So you have a lot of hypotheses, right? You're a scientist. You can't just be like, it's husband for sure. I know that I watched enough TV shows husband. You can't just do that. You can just, well, she could be murdered by her husband, or she could be murdered by intruder, or she could be murdered by the alien. Entirely possible, right? You never know in this world, there might be the alien come out from the sky and this X-File all over again. And her husband is abroad and like he had nothing to do with it, even though he liked to kill her, but he couldn't. So, and our job is this. You come up with this hypothesis and you test it with the belief and the observation and see which one is more likely. Same thing here. And you look at this data and you be like, okay, so she's dead, she's murdered, and she was abused by her husband before. And the fact that her husband is gone from the scene and not to be found, is likely that this would be true. So the probability of this being true, probability that this is true is actually pretty high. As opposed to like, well, She could be murdered by the alien or the Asgardian or Thor. I don't know. But there's is mathematically there's a probability that this will be true as well, but it's so small because we don't even know this alien exists yet, right? So the same thing here. So we use the same idea here that we have the DNA sequence is our observation, and there's our belief we have the something that model we call model of molecular evolution. We have some knowledge of how mutation works, that mutation should work this way, or we think, and we have all these trees as hypothesis, and we test them with our belief and our observation. So you might choose tree number 1 as your base tree. So by base is basically is most probable with data and belief. It depends on how you believe DNA behave, and there's multiple ways and people come up with that. There's more than one belief, right? Just like our religions, the world works the way it works, but some people believe that God created this. Some people believe that no, not God, something else created it. So it's like, but the world works the same way. The world doesn't care what you believe, right? The world goes on. Same thing here. You have your belief, and you have, but there's a fact. And the best tree is the tree that consistent with your belief and consistent with your observation. So let me remind you right now, I'm gonna say this like so many times, that all the phylogenies are hypotheses. They're not real. They are estimation of what we think, believe to be true. So you can do the same thing with your friends. You can try to answer the same question. You walk in, you see a murdered woman, you firmly believe that she murdered by her husband, but your friend is a big fan of X-Files, so she's gonna believe the alien story for sure, right? So it's kind of, observation is one thing, but when you change your belief, your model, then the answer may change, may or may not change. Okay, so how does the character-based method works? So let's see if you have this 10, so we have 3 organisms here, 1, 2, 3, and they're different by 1 base right here. So in the distance-based method, this will be different by 1, this will be different by 1. Done. So these 2, organism number 1 different from organism number 2, the same amount that they're different from number 3. But if you consider the base change, so we have transition, right? Which is change from one same type, from pyrimidine to pyrimidine, from purine to purine. So like 2 rings to 2 ring, 1 ring to 1 ring, that transition. And you also have transversion, which is the switching between different types. And which one you think would be more difficult to do, right? The one that changed from 2 ring to 1 ring and 1 ring back to 2 rings. So maybe let's say this is a gymnastic, do the backflip, right? The transversion, you get 10 points. Beautiful backflip, 10 points. And then the transition, just like jumping, easy because you change from 2 to 2 rings, easy. So you get 1 point. Easy to easy. I want something difficult push like that, right? So let's see, A to C change from A to cytosine. Oops, sorry, not A to C, sorry. G to A. G to A is a transition, only get 1 point, too easy. But if you change from G to C, you change different type, this get 10 points for being difficult. So if you think like this, if you believe that change from 2 ring to 1 ring is more difficult, then it's less likely that 2 and 3 are correlated because it's more difficult. Like this is more natural. So if you draw the tree, 1 and 2 would be related and 3 would be farther apart because the farthest out. So that's the idea. So you give the weight to different type of characters based on the difficulty of mutation. And this difficulty scoring system is called nucleotide substitution models. This is so this is the belief of how uh, mutation or substitution occurs. So what do you believe what happened with the substitution? So there's a lot of models. There's like 20 something models, and there's a few that you can use. There's a few that you should know, and I mean this will come in handy later on. So the simplest model is called Jukes Cantor, is discovered by Mr. Jukes and Mr. Cantor. So he believed that all rate are all change are the same. So this is basically the distance-based method. It's the same thing, right? Because we assume all changes to is the same. A change to C is the same with A change to G is all one rate alpha. That's done. That's easy. There's one rate, and the simplest model is easiest to work with. But if you believe in that transversion and transition have different rate, so A to C is one rate, but A to G is a different rate. So this is called Kimura model, or KAD. It's a two-rate or two-parameter model. This one gives a transversion one rate and transition another rate. So there's only two rates, one for transition and one for transversion. And of course, you can like subdivide models into further stuff. And the most complicated model you can have is GTR, General Time Reversible. Basically, if you change from A to C, you get one rate. You change back from C to A, it's different rate. So it's all different. So you can have all different rates. So like it's almost like you can, I think you have this feeling before, right? You go somewhere, it takes forever to get there, but we come back home, it feels much faster. That's the same way, right? It's basically like going back, and even though the distance should be the same, but it feels different. The same thing could happen with the DNA as well. So you can choose whatever model you want. And the reason behind it is that you go from this simple model to this model. It's a lot more computationally intensive. Like back in the day when computers are not so fast, this would take forever to compute. And that's why you have to pick the model that's most consistent with your data and require least amount of calculation. So luckily, there's a way to do that. There's something called model selection in our program. So you don't have to think, you just click and they would pick the best model for you. Easy, right? So they will show the table look like this. They'll compare all 24 different models, and the top model, just like American Next Top Model, right? The top model is the best model. So the best model is the one with the highest likelihood. We're going to talk about likelihood in a second. And the lowest AIC. So for those of you who hate stats, I hate math, but I love stat. I love stat, but I'm stupid at stat. Does that make any sense? I don't know. It's like I think it's so awesome, but I just so bad at it. So just humor me here. It's just like the AIC, the smaller the better, and the likelihood the higher the better. So this one is highest number, is the smallest negative, so it's highest number, and this is lowest number. So this is the best model. The TN93 is the best model. So if you like blah 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 Ajahn Bia blah 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 blah. So if you feel like that, just pick the top model. Okay, top model, like the top line. That's the best model they choose for you already. So this is and in the program they give you the full name of the model, Timurane 1993. So you will learn more about that when you do the programs, right? And tube is right, stat is inevitable in bio. You can avoid it for a long time. You like me. Side story, I never took stat in my undergrad. Like in my curriculum is so weird. They require 2 semester of calculus, but they don't require stats, which is like, what? And I walk into my PhD and feel like a fraud because everyone else knows that already. So I have to go back to not sit into audit, not even audit. Actually, I took the undergrad class again and struggle to compete with undergrad. Like they're so, like all those undergrad are so smart. I took 2 semesters of statistics to keep up with undergrad, and I get lower grade than most undergrad in that class. So just like, oh my God. So learn stat now, better than later, and you'll be so popular. If you think the job market is so difficult right now, if you are bio person who knows that, you'll be like, go. Be like, oh my God, I want you right now. Like seriously, there's people who like, because most of scientists, most of biologists, like my colleagues, they hate stats. They're like blah 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 math number, and they're like, oh, I can't do it. So they hire someone to do it because they have money. So be the person. If you yep. Basically, Tube is right. Read Tube's comment. So basically, be like Tube. Okay. So that's how we do it. So let's go through each of these methods, how they work, and how they kind of give different flavors of the use of this belief. So the maximum parsimony. So the word parsimony, believe in simpler is better. So parsimony is like one of those things that like really kind of it might sound too good to be true, but we believe that simpler things are actually the better one. They believe that in nature work simply. They work in the simpler way. For example, I'm here in Kasesa, right, which is North Bangkok. I can go to Salaya by driving, right, which is easy. I can drive an hour to up 45 minutes to Salaya, or I can take a plane from Don Mueang Airport to Suvarnabhumi and take a boat from Samut Prakan down to Singapore and back in Burma and go to Salaya. I could do that, right? But why would I do that? It's ridiculous. It's not simpler, but could I do that? Yes, I can. I'll probably take about 2 days to get to Salaya. I'll get that too, but it's not going to happen. So we believe that most of things in life are doing simply ways. So this is maximum parsimony. So we believe in the simplest model, basically. So how does it work? So let's look at this alignment. So we have this position that there's only one, either there's only one apomorphy, everyone else is different, or everyone else is different. This is SNP. And this side or this position are considered non-informative because you can divide them into groups. It's not really helping us too much, right? It's like it's not divided equally, so it's not informative. And the informative side is the one that have at least some synapomorphy. So you can see synapomorphy here. Synapomorphy. And you might argue that, well, this is a synapomorphy too, right? But the C here is all by itself. So you have one synapomorphy and one apomorphy. That's not helpful. So you should have in that same position have synapomorphy for both groups at a minimum. So once you have that, we're going to consider only this position. The others are not helpful, so we're not going to think about them. So we look at position number 7 and number 9, and there's a GGCC, right? At the tip, there's GGCC. and you imagine the scenario, oh, G and G probably come from the same ancestor, which is also G, and C come from the same ancestor, which is C, and there's zero change. And there's only one change from G to C here. So the total number of change, if you use this tree, use this relationship here, is 1. Okay, the number of mutation required for that to happen is only 1. But if you change that a little bit, let's say you want tree number 1 and organism number 1 and organism number 3. I'll change the color. Organism number 1 and number 3 to be related. This is G, this is C. So for this to happen, let's assume that the ancestor is G, so you require 1 mutation here. And you put 2 and 4 together, the same thing here. You require 1 mutation here. And from ancestor to ancestor, there's another 1 mutation here. So for this to happen, that would be 3 mutations. So you can see that if I pick tree number 1, it's like me driving to Salaya campus. Easy, straightforward. This is me taking the boat from Gulf of Thailand to Singapore and back to Burma to Salaya. This take a long time to get there. That's probably not the right answers. So in the end, you pick the tree that have the least number of change. You do that with every position. And in total, tree number 1 have 2 mutations, require only 2 mutations. And that's your best tree. That's what they call the most parsimonious tree. So the most parsimonious tree, the best tree is require the least number of base change. Okay. So you just do this and you can see that slightly different now. You kind of like put the random tree configurations and you compare the number of change that require for that to happen, and you pick the easiest one because you believe that this would be the way to go. And that's not wrong of you to assume that, but might be too simplistic. And there's a lot of people who feel like, come on, I mean, sure, like you should not have to like take the boat to Singapore first and go to Salaya. That's ridiculous. But you could also, let's say, have a private jet, helicopter. It sounds more expensive, but you could go to Salaya a lot quicker even, right? Not the simplest way to go, but definitely a quicker way. So the world does not always work in the simplest way. And some people feel that this is oversimplification. So there's some smart cookies in the math world come up with this called maximum likelihood. And the actual calculation of likelihood is a bit convoluted, but I'm gonna try to break it down simply. So let's say we just have one position, right? A, G. Just look at one position, and you assume that, oh, these two have A's, so 1 and 2 must be related, and G is probably separate. So this is your hypothesis. This is your hypothesis. What happened? So what you're gonna do is to try to come up with who's ancestor for 1 and 2, who's ancestor of 1, 2 with 3. In the scenario 1, this is A, because it should be A, right? Because both of the ancestors are A, and this should be, let's say if this is also an A, and you're like, no, that probably should be G. Like, you can calculate those probabilities. So you do calculate the probability of A change to A change to A, and probability of this become A, and probability of A change to G, and probability that this is A, and you use all these numbers, and sum them up. You sum all this up, and this becomes your likelihood. So, and you do different scenarios, and like, it keep repeating itself. So basically, you try to fit different hypotheses or different scenarios into the same data on your tree and see what the likelihood is. So you do it this different ways, and in the end, you compare the likelihood score that come out. So you provide the tree that, you find the tree that, and you do this with, oops, sorry. Every time click the wrong buttons and it went away. So you do this not just, so in the previous slide, we do only for one position, right? This is position 1. You do this with position 2. Every position of your base is just like, you're like, oh my God, do I have to calculate this by hands? The answer is no, I did not do that. And you will not have to do that. Took might have to do that, but no one else has to do that. So you multiply all of them together, and that's become your likelihood of the tree. And you can see that this configuration of 1 and 2 together, and 3 being the farthest one, have the highest likelihood. So this one have maximum likelihood. And I choose you because given all very, like, the probability of every single position being consistent with the tree, that tree is more consistent with my data. So, but the bottom line is the maximum likelihood find the probability that the tree that you created is consistent with your data. And the one the most consistent with your data is the right one. So I use the word consistent. I don't say it's correct. It's consistent with your data. And the calculation of those probability based on the model of substitution that you choose. If you choose one rate Jukes Candor, it gives you one answer. If you choose GTR, it gives you different answers. So it's kind of based on your belief, just like the murder case. If you believe the husband is a horrible person, then you probably go that route. If not, then you go the other route. So that's the idea. So that's, you choose the best tree with the best likelihood. That's called maximum likelihood process. Okay. So again, if you want to calculate the likelihood, you could. There's a computer program to do it for you. You don't have to be able to calculate that yourself. You just understand the idea. And if you think this is complicated, welcome to the last one. This is the worst. This is called Bayesian inference. It's based on the guy named Bayes. And Bayes is an old man from 300 years ago. 300 years ago. And for some reason, we just thought of him now, because what he proposed is this. This is Bayes' rules. The probability of the tree given, this symbol is given. The probability of the tree given the data is the probability of the data given the tree times the probability of the tree divided by probability of data. And you'll be like, what? Yes. I have the same feeling. So basically this. So you, in a nutshell, there's a whole thing called Bayesian statistics, and I'm not trying to like walk into that like dangerous zones of like killing you in the process. You'll be like, this is the worst 2 nightmare in a row, right? We have molecular biology nightmare, and now we have statistic nightmare. And yeah, I'm sorry. Sorry, not sorry, really, but essentially what it does is this. So let's say you can calculate this number. You can calculate this probability, okay? And you do this. So imagine you'll be this person walking uphill, but blind. Have to work on with me here. You blindfold yourself. I don't have the blindfold. I should have prepared for it. Okay. I walk myself blindfold here, and you're gonna walk up the mountains. So if you blindfold and you walk up the mountains, so you step your foot, right? And if you feel your foot going upward, you're like, okay, that's uphill. And if you go the other direction, you're just downhill. So you keep going uphill. So this is probably the same thing here. So you start with the tree that, okay, let's say A and B are related and C are not. And then you're like, you know what? I'm going to change my mind. Let's say A and C are related and B are different. And you feel like your probability is going up. It's like, yes, I do the right thing. Just like if you go on diet before, this is going to sound familiar. Like you exercise all you want, right? And then your weight is not going down. It's like, oh my God, I run every day and I still like weight the same. Something is wrong. Let's change the diet. Let's stop drinking milk tea for a day and you drop 10 pounds. Like exaggeration. So same thing here, like you change the tree and it's like, they're probably going up. You're like, woo, yeah. I'm getting the right answer, right? So you keep doing that again. You're like, okay, let's do that. I think I'm in the right area. You know that A and C together, but the branch are probably really long and B is really long branch. And you calculate the probability of this tree and it keep going up. It's like, yeah, better answer. And you keep doing this. You keep tweaking your trees, like, and you like blindfold yourself. Like, oh, is it better? Is it better? Is it better? Is it better? And you're like, I don't know. And this whole process is based on whether or not you want to go next. And this process is called Markov chain Monte Carlo. There's two parts of this. Monte Carlo basically is a fancy name of randomization. It's the reason called Monte Carlo because it's referred to the gambling on the island of Monte Carlo in the coast of France. So it's a big casino. So the Monte Carlo is called randomization. And Markov chain is regard to previous result. So you randomize your direction up the hill, but based on the result you get from the previous one. If you feel like you're getting better, you keep going up. If you step your foot and it's not going higher, you stop. Okay, so like you blindfold yourself and you're like, if it go up, and keep going. If it doesn't go higher, then you stay the same and you find the new directions. So this is why I call Monte Carlo, Markov chain Monte Carlo, right? So it's keep going. And once you're at the top, right? On top the world, on top the world. You walk up like on the hill and you're like, there's no place getting higher. Like you walk and walk and walk and walk and so you can't find a footing to go higher places. It's like that. Yeah, the local maximum. You're at the top and you cannot go further. And everywhere you go is only lower. It's only downhill from here, right? So you know that you're at the top and this is the place you want to be. I'll answer two questions a little bit later. So the idea is that you keep tweaking the trees, right? Until the tree reach this. This is your walk. You keep walking, you randomly walk. And at some point you start to like walk in the same place. You walk at the top of the hill. You keep walking, walk. And then instead of picking the best tree, because you're at the top of the hill, everything at the top of the hill is so good, right? Like why choose average? So the best tree is average of all these best tree together. And there's a algorithm to average this out. This is beyond the scope of the class. But basically, instead of choosing the best tree, you kind of average out this best tree. So the result of this tree is called MCCT, maximum credibility tree. The tree with the maximum credibility. Very Bayesian talking. It's like the on opposite from molecular biology, people love to use normal English and make it so weird. Like use the word credible all the time, use the word likelihood all the time, but when in stats, it's mean something completely difficult and weird. So just hear me out. Once you get at the top of the tree, or the top of the hills, and you like average all the trees that you get up there as your base tree. It's not one single tree. It's a component of everything. And two, asking the question that you might get from calculus, because when you walk up the hill, right, you basically like, I'm here already, right? And you because you're blind, right, you don't see that such a higher peak up there. You might feel like, this is good. I feel nice. I stay here. When the actual answer is here, because you're blind, it's not your fault. You're blind. How you solve the problems? Think like a traveler. So if you stuck at what this is probably called local maximum. So this is the same problem with calculus. You can have local maximum. You can have the maximum at the smaller peak, but not the global one, not the highest one. The easiest, this is really weird. The way you do it is to keep walking, like Johnny Walker. You walk longer. Because if you keep long enough, you feel like at some point you're gonna fall off the hill and you're gonna walk again. And you probably end up at the highest hill. And in the reality, what in this kind of analysis, the MCMC, they call MCMC chain. This process of walking is called chain, and they kind of let 4 people walk at the same time. They start 4 different chains at the same time, and they tell these 4 people to walk differently. So the first 2, you walk slowly. You step like you really use really long step. The other one, you walk slowly, meaning take a small step. And the other 2, like walk quickly, like run blindly. So, and the hope is these 4 people end up colliding each other at the top of the hill, like, boom, like, oh, here, good, I'm in the same place. So that's the hope. So basically, to avoid the local maxima, local top, you use more people to run and walk, and hopefully they get to the same place. And obviously, most of the time, this is true story from my work, they don't end up at the same place. They'd be like, the slow one over here, the fast one over here. And they're like, dude, what's going on? Like, we don't find each other. So have to keep running. So the minimum I run to get the feasible result is 10 million generations for it to get the right answer. It take about, on your personal computer, take about a week to do so. But if you use supercomputer, it go a lot faster. But that's why people wait so long to do this calculation. And for the sake of simplicity, we will not cover this method in this class because it's computationally intensive. And I think you get the same idea, but I don't want us to caught up in the computational intensive. Yeah. Not initialization, like the whole thing. Yeah, the whole run. Like there's a different initialization too, but yeah, the whole thing is you need at least 10 million or something in the scale of millions. So to sum this up, if you use parsimony, you just count change, and you pick the tree that have least number of change. And if you are ML, maximum likelihood, you pick the tree with the best likelihood. You calculate likelihood for each tree, but then if you Bayesian, then you find all the possible tree, and the tree at the top of the hills, you use them all and you average them and you call them MCCT. Okay, so that's the different idea. So once again, if what I say in the past 20 minutes are blah, 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 look at this table. And remember that all this probability or likelihood based on how you believe in the substitution model, right? Like if you believe that all the rates are different, then you have one answer. If you believe that all the rates are the same, another answer. And based on this character-based, this is character-based method. All right. I know your brain probably already fried right now, but we're gonna keep pushing a little bit more, and then we'll have a bigger fatter break this afternoon. So